This machine is the ORION-1, an 8-bit CPU heavily inspired by Ben Eater's 8-bit CPU. It has 16 bytes of memory and can perform addition and subtraction. That's just about all it can do, so I made it run the Fibonacci sequence. This video is going to be for people who don't understand what I just said, or do and want to learn how it works. It took about 3 weeks to actually assemble, probably because of how much I kept procrastinating. I've never done any electronic logic with ICs before, only building the occasional robot with an Arduino. The tools I started out with include a multimeter and a DC bench power supply. I'll go through what each module does very briefly, but if you want to actually learn what the chips do and why they're connected that way, I'll post some good resources. The clock module generates pulses at a regular interval, which I can specify with this potentiometer. It also has another mode that lets me manually make a pulse whenever I click this button right here. Imagine the bus as a tiny yellow school bus that drives from one module to another on this little highway. At each stop, it picks up 8 kids and drops them off at their destination. That was called an amazing metaphor, and this is the actual bus. The highway is this breadboard, the kids are logic signals, and all the bus stops are other modules. Registers store 8 bits of data and output them later when I want to read them. This is kind of like a row of 8 coins, which I can flip to latch a value, and I can just look at it to read the value. General purpose registers are registers that anyone can use to store the data they're working with. Special purpose registers are hooked up directly to another module and they affect how it functions. The A and B registers are both special purpose registers and they are hooked directly into the ALU, which I'll get into next. ALU stands for Arithmetic Logic Unit. This module does just that, math. This one specifically, however, is probably the most basic you can get. It can only do addition, and by using a clever hack called 2's complement, I can also subtract 2 numbers. The 2 numbers it adds or subtracts are the numbers that are in the A and B registers, which is why they're special purpose registers. The Flax Register is a special purpose register that's hooked up directly to the ALU and the control logic. It knows if the ALU is outputting a 0, or if the output is too big for the ALU to hold. It can then give that information to the control logic for conditional statements. The output register is another register exactly like the A and B registers, except ironically, it can't output to the bus. It's actually hooked up to this 4 7-segment display driver, which displays whichever number is in the register, so it outputs whichever number I want. It also has 2 modes, so I can display positive numbers or 2's complement numbers, so that's cool. The last register is the instruction register, or IR for short, which can input from the bus and can also output to the bus, but only the least significant nibble, or LSN for short. The reason for this is that this computer can only support 16 instructions, which fit in the most significant 4 bits of the instruction, and if I want to pass in some data with it, it would need to be done so using the LSN. It is also hooked up to the control logic for the computer to actually execute the instruction, making this register a special purpose register. The control logic is the part of the computer that actually makes the computer work. Each module itself can do its own job, but it's meaningless unless they do it in a certain order. The control logic I use is called microcode, which is a fancy word for each instruction is broken down into a bunch of steps. The steps are shown here with these green LEDs. The instruction register is right above with these 8 blue LEDs, and the leftmost 4 is the instruction that I'm executing. The steps along with the instruction go into these EPROMs as addresses, and they output whatever modules should be active at that point in time. This is probably one of the most complicated parts of the computer, according to me, so it'll take its own video to properly do it justice. RAM stands for Random Access Memory, and as the name implies, lets me randomly access memory. Imagine it like an index card with a grid on it, and I can read any number on it, but only 1 row at a time. I can also write any number to it, but still only 1 row at a time. Also, when I turn it on, it starts out with random garbage in it, so I have to reprogram everything inside after I turn it on if I want it to do stuff. On this CPU, reprogramming is manual and is also a massive pain, but usually computers reprogram the RAM itself when they turn on. This RAM is 16 words by 8 bits, which means it can hold 16 bytes, which is almost enough to install Tom Clancy's Rainbow Six Siege. You thought there were no registers left, but I lied. There's actually one more. This one tells that index card which row to read from or write to, so it's wired directly into the RAM. It's called the Memory Address Register, or MAR for short. It's kind of confusing because MAR and RAM are each other backwards, so think of it this way. What's likely to physically hold more stuff? A $30,000 pickup truck or a verb? That's right, RAM can hold more data. And I lied again. As you can probably tell, registers make the world go round, so here's another one called the program counter, or PC for short. It's pretty much a normal 4-bit register, except it has the ability to count up 1 in binary. This one tells the memory address register which instruction to execute. And last but not least, we have the reset button. This button just resets all the modules on the computer. I have ideas for upgrades to pretty much every single module here, so I'll slowly but surely make progress on them. I also plan on making PCB designs for the breadboards. This will make them slightly smaller so I can reclaim lost desk space and work on them at the same time. Also, I've never designed a PCB before or done any surface mount soldering, so it's kind of a learning experiment. If you're interested in making this computer, good luck, it's a fun project. Alright, I hope you learned something cool. Bye.